So in this video, we're going to pick up where we left off from the last one and continue just a few more questions from Math Excel in this final review that leads up to our Unit 4 test. In this example, we're being asked to find the volume of a right circular cylinder. Now, as prior knowledge or previous knowledge, we're told that the volume of a cylinder, so I'm thinking of a cylinder that looks something like this, is dependent on both its radius and its height. Well, I think it would be kind of nice if we could compute the volume based on just one of those measurements. And as it turns out, the height of this particular cone is going to be 4 times the radius. So if we think of this for just a second in terms of function notation, we can say that the height of the cylinder is based on its radius, and that happens to be 4 times the radius. We also know that volume is based on, well, 2 variables here, so maybe I won't write it that way after all. But if I allow for the height function, h, to substitute in place of this variable h in the volume formula, we're going to end up having a volume function based on only the value r. So pi r squared times 4r, so 4r instead of h. Now we have a volume formula, and I'll write that it's the volume based on radius, which is equal to 4 pi r cubed. So the 4 times pi, those two are coefficients that I'll multiply together and leave them in 4 pi notation. And the r squared will multiply by this r to give us the r cubed. So as long as we're dealing with a right cylinder whose dimensions are always in proportion to one another, the radius is always 4 times the height, then it doesn't matter the specific size of this cylinder. Evidently the volume, when computing for a cylinder of this ratio, will always be 4 times pi times radius cubed. Now to switch gears and talk again about functions and their inverses, here we have a function f of x equals x squared minus 3 over 5x squared, and our objective here is to find the inverse and check our answer. Now it's important to note that this function is a one-to-one function. That means that its inverse will also be a function. And the process that we went through in class to determine that is to change the variables to y and x. So we have now x squared minus 3 over 5x squared equals y. Then we reverse the x and the y coordinates. So now I have y squared minus 3 over 5y squared. And then it's our next objective to isolate y. And we would use any algebra tricks that are necessary in order for that to happen. Now what I notice is that I could multiply both sides of the equation by 5y squared. And that's going to leave me with y squared minus 3 on the right and 5y squared times x on the left. Then I recall another technique that's going to be helpful. If I bring all terms that contain a y squared to one side of the equation, I would end up with a collection of terms that all have the y squared term common to them. It'll act as a common factor. So I'm subtracting both sides by y squared, and that leaves me with negative 3 on the right-hand side. So here again, this term and this term are separated by a subtraction sign, and both of those terms have a common factor of y squared. So if I factor out the y squared, I'm left with 5x minus 1 equals negative 3. And now to further separate the y components, we can divide both sides by 5x minus 1. And then take a square root of both sides of the equation. And we've now isolated y. And y would be equal to the positive and negative result of the square root of negative 3 over 5x minus 1. And it's worth noting that this x value that we just solved for is a new, this y value that we just solved for is a new y value. This new y value does represent the inverse of the original function. Essentially, as soon as we made the switch all the way back here, this new y coordinate this new y component ended up becoming our inverse value. So when I report my final answer, I would like to have f inverse of x equals positive or negative square root of negative 3 over 5x minus 1. Now, we do need this plus and minus sign here because we did place the square root symbol into the problem in order to solve. And if I was looking for a complete inverse of the original problem, I would need both components. But I did overlook this note here that we're really only interested in x values that are positive in the original function. Therefore, we're really only interested in y values that are positive in our final answer. And so the only way that we'll get positive results out of this square root is if we ignore the negative component and only keep the positive square root. So for a visual reference on that, here's the graph of the original function. And if I incorporate a domain restriction, we can indicate that x must be greater than or equal to 0. So now we've got our domain restriction. This is indeed a function that is one-to-one. If we graph our inverse function, I pause the video to type that in. If we show the inverse function, g of x, we'll call it in this case, it does appear that this function is the inverse of the original. And we know that it's an inverse, or it appears to be an inverse, I should say, because it does appear to be a reflection over the y equals x line. If I were to pick any coordinate along this red graph, then its opposite, or inverted coordinate, should appear on the blue graph as well. Now, if we go back to the picture of the equation before I introduced the domain restrictions, you'll see that there were two branches to the graph in red. And this complete function is not one-to-one because it fails the horizontal line test. Watch what happens if we introduce not only the positive square root of our inverse function, but the negative square root as well. Now, it may take some focus here, and I'm going to change the colors for just a second. Now, maybe this will help just a little bit. The inverse line is now a dotted line, and both branches of the inverse function are the same color. Does the graph in blue appear to still be a reflection over the y equals x line of the graph of red? And I would argue yes. Now, if I look only at the blue function, well, you might recognize that it's not a function at all. So when we were talking about inverses, we said that functions had to be one-to-one in order to have an inverse. And more correctly, we would say that the function has to be one-to-one to have an inverse that is a function. In this case, our original function in red is not a one-to-one function. Therefore, its inverse is not a function anymore, but rather a pair of equations or a relationship that creates a graph that violates our vertical line test. So hopefully that clarifies a few things, or at least gets you thinking about functions and their inverses a little bit more carefully. So I'm pretty satisfied with the work we've done so far. I do think that this equation is the inverse of the original. Whoops. So this equation is the inverse of the original. Now, one of the instructions does tell us to check our answer, and I'm not entirely certain how MathXL has you check this, but on a handwritten test, we should recognize that we are going to compose our functions together. So we're going to take f and compose it with f inverse of x, and we hope that that's going to end up equaling x. And we should also do the same with the composition in the other order. We should compose f inverse with f at x and hope that that also equals x. Both of those statements have to be true in order for us to check or to verify our answer. So I went ahead and did all the work here for this check, and I'll walk you through it real quickly. I started with my outer function f of x, which would have been something squared minus 3 over 5 times something squared. The somethings in this case ended up being the inner function, the inverse that we calculated, so the square root of negative 3 over 5x minus 1. In the act of following the order of operations, we would have to square each of these arguments, and when you square a square root, that essentially just eliminates the radical symbol. So we have this expression, negative 3 over 5x minus 1 minus 3, and 5 times negative 3 over 5x minus 1. In the numerator, I'd like to have common denominators to add or subtract fractions together, so that's what I've done here. I've multiplied in the 5x minus 1 in both the numerator and denominator of this fraction. And in the next step, I'll just go ahead and talk about it while we're here. I thought to myself, well, negative 3 take away negative 1 turns in, negative 3 take away 3 times negative 1 ends up being 0. And negative 3, well, we've already combined those like terms, but now we have a negative 3 times 5x, which produces negative 15x. So that takes care of a lot of the numerator work. If I focus on the denominator for just a second, I have 5 times this fraction. Well, that turns into negative 15 over the denominator. And again, we'll carry that through down below. And once we get to this point down here, we may notice that we have the denominator of the numerator fraction and the denominator of the denominator fraction are the same, so those will cancel out. If you want proof of that, you can think of the top fraction being divided by the bottom fraction and use appropriate methods to combine those two. And then we're left with 0 minus 15x, which I'll just report as negative 15x, divided by negative 15. And certainly negative 15x divided by negative 15 does indeed equal x. So we've now verified the inverse in this direction, but we also need to verify the inverse in the other direction. So I'm going to challenge you to try this one on your own, and you can pause the video now to give it a try. Resume playback in a moment to check your work. And so the substitution that I would make in this order is write my outer function as f inverse. So the f inverse function was the square root of negative 3 over 5 times something minus 1. The something that we're evaluating happens to be my inner function, which was x squared minus 3 over 5x squared. And in the process of simplifying, I know that when I multiply in this coefficient of 5, it's going to cancel with one of these 5's, and we're left with x squared minus 3 over x squared in that position. I would like to combine these two numbers, and in doing so I needed a common denominator, which I made x squared. So I changed the minus 1 to negative x squared over x squared. When combining, I retain the denominator of x squared, and I have a numerator, x squared minus 3 minus x squared, so the x squareds end up canceling out. And now we have the square root of negative 3 over x squared. Well, if I carry that up here because I was running out of room, I could think of this negative 3 dividing this negative 3 over x squared. And in the act of dividing by a fraction, I can multiply by the reciprocal. So we multiplied by x squared over negative 3. The negative 3 and negative 3 here will cancel, and we're left with the square root of x squared, which indeed is x. So by composing the function f with its inverse and obtaining an x as a result, and then composing the inverse with f and obtaining x as a result again, in both cases, that's enough to verify that these two functions indeed are inverses. Now visually we had a pretty good assessment here. I mean, we recognize that these appeared to be inverses. I think we were pretty confident going into it, but now this process certainly proves that those two are inverses, and we have now had that mathematical rigor to establish that that is entirely true. Let's go ahead and do one more problem and call it quits for this video, and we'll talk about an application of inverse functions. So the first comment in this problem is just a little bit about vocabulary. We typically use f with a -1 exponent to indicate inverse. However, if we start using letters to represent functions in a more, I don't know if appropriate is the right word, but if we use them in an abbreviation manner, we can actually just simply reverse the two letters, and that would be sufficient to identify our inverse as it is. So what we have is a problem here that calculates the distance in feet that a car requires to come to a complete stop based on r being the rate of speed. So we have d of r given to us. What we would like to have is r based on d. So if we would like to calculate the distance based on the speed that someone's traveling, we could use this function. If I would like to calculate their speed based on the distance that's necessary for them to stop, we would use then this new function. And we should go ahead and calculate that. Now, there are a variety of ways that we can find the inverse, but what I like to do is, of course, use y equals notation. So I'm going to change this to y equals 6.97 times x. We can change that to x minus 90.46. Then I will switch the x and the y terms, or variables, and solve for the new y. Now keep in mind, this new y value is the inverse that we're going after. So when we're done, this y is indeed going to represent the r function that we're after. So to isolate x in this case, to isolate y in this case, it's pretty straightforward. I think we'll add 90 to both sides of the equation to move it to the left. Then we'll divide by 6.97 to isolate the y, and we'll find that the new y, I'll put quotes around it just again to be clear that we're talking about a new y. This new y value is going to be equal to x plus 90.46 divided by 6.97. Now if we use our notation, this new y is the inverse of the original d of r function. So we'll call this one r based on variable d, which is equal to d plus 90.46 divided by 6.97. If I was working out in the field and I knew this formula represented the distance that a car would stop based on a person's rate of speed, then I can use just the opposite. This formula will calculate the rate of speed that the person was traveling based on the distance that was required to stop. Now, anytime that we calculate an inverse, we should verify that the two functions are indeed inverses, so we can do that now. So in the first check, we should compose our outer function d with our inner function r of d. So we're taking the function and composing with the inverse. And if you didn't notice here, since our variable is d, then when simplified, we should be left with just a variable d. Let's see if that works out. Okay, so this one looks like it checks out. If I took the original function d as my outer function and my inverse function r as my inner function, then the 6.97s will cancel when I distribute this 6.97 in. And then as I combine like terms, I'm left with variable d. We should check in the other direction as well. And we should take our inverse r and evaluate it at d of r. This time, we should end up with the variable r when we're done. Now, in our last few examples, we always solved to see if it would end up equaling x, because that was the only variable we used in both the inverse and the original function. But in these functions here, the variables ended up changing. So that's why we're going to have r as our target this time. So let's see what we get while checking our answer this time. And it appears that this one works out just as fine as well. So when composed in both directions, we end up with our single variable, so either r or d or x, whatever the variable may be. We've now found our inverse function and checked it twice, so I think we're in good shape. I'm happy with this r of d to represent the inverse of d of r. Hope these series of examples helped you out a little bit further and gave you perhaps a different perspective to think about some of the problems, or at the very least clarified any of your concerns. If you've got other questions, please let me know. Reach out to me either through Schoology, through email, or talk to me in class. Thanks for watching.